Today I'm going to talk about Bratteli-Vershik representation of minimal Cantor systems. And this is a way to represent minimal Cantor system. This is always for C actions. This is a way to represent minimal Cantor systems using infinite graph. And this infinite graph were introduced yesterday by the first speaker. And everything that I'm going to talk today is written in that paper, Herman Putman Scout from '92. And first, I'm going to start introducing the concept of Bratteli diagram. I'm going to recall this because this was introduced yesterday. Where is a Bratteli diagram? This will be an infinite graph that I'm going to denote like this. V is the set of vertex, and E the edges. And we can make a partition of the set of vertex a countable partition, the same for the edges. And they have the property that every Vn is finite, every En is finite, but also the first set of vertices has only one element. The other one, they are finite. Every set of edges En is finite. And in the set En, we have exactly the edges that start from Vn and which arrives to Vn plus 1. So En is the set of edges starting from Vn. This means source edge, and arriving. This is the range, arriving to Vn plus 1. So if we try to make a picture of this, so the Bratteli diagram, they look like this. So at the beginning, you have the only vertex in V0. Then you have the vertices in V1, then in V2, and so on. And then the edges, they are always between consecutive set of vertices. So here you have the set E0. Here the edges in E1, and so on. So this is the picture of a Bratteli diagram. So you have to imagine that this is continuous. And when you have a graph like this, you can define matrices, the incident matrices. So for every level, for example, between B0 and B1, we can define a matrix in this case for, okay, I'm going to define this here. So the sequence of incidence matrices for the Bratteli diagram B will be a sequence of matrices AN, where AN has Vn plus 1 rows. So the number of elements in Vn plus 1, and Vn columns. And in the coordinate V prime, you have the number of edges from B prime to B. So this gives you a sequence of matrices with coefficients in the positive integers. The Vn are disjoint. Yeah, this is disjoint. Thank you. Everything is disjoint. Yeah. So, and every time when you have a sequence of matrices like this, you can construct a Bratteli diagram. And okay, and we will consider Bratteli diagrams which are simple. I'm using maybe the same terminology than in the previous talk. We are going to say that the Bratteli diagram is simple okay, another thing before to define this. When you have a Bratteli diagram, you can make you can construct another Bratteli diagram taking subsequence of vertices. And instead of taking the edges of the Bratteli diagram, you take the path from the subsequence of vertices. So before to write this, I'm going to say that a new Bratteli diagram, B prime, is a telescoping of B if there is a subsequence of integers like this, in order that the set of vertices of B prime, that I'm going to note like this, such that Vi prime is just the set Vni of vertices, and Ei prime contain one edge from every path from one vertex in Vni to Vni plus 1. So I'm going to write this, I don't know, the set contains one edge from every path from Vni to Vni plus 1. So this is like a way to, so if you think, here we have the same information than in B prime. And we are going to say that B is simple if there is a telescoping with strictly positive incidence matrices. So the incidence matrices of the telescopians are just the product of the incidence matrices of the previous Bratteli diagram. So we are interested in Bratteli diagram where you can think from the level Vn, you can go to any vertex to the level Vn plus 1. This is the idea. This is simple. And from here, we are going to define now the set of infinite paths, like yesterday. So xb will be the set of all the edges, the sequence of edges. which are paths. So that means that the vertex where En arrives is the same vertex where En plus En plus 1 starts. This is the set of infinite paths. And you can put a topology here, like yesterday. So in every En, you put the discrete topology, here the product topology, and then you get something which is totally disconnected and closed, so compact. And there is a way to avoid isolated points because we would like to have a Cantor set here. For example, if B is simple, you can think of a simple Bratteli diagram just thinking about strictly positive matrices. So if B is simple and XB is infinite, so you will get a Cantor set. So this is the way to ensure that this will be a Cantor set. So, and we are going to work with this kind of Bratteli diagrams, always simple, and this set always infinite. And now we would like to define some transformation here. Now we have a Cantor set, and we would like to define a transformation from XB to XB. And how we can do this? And the way to do this is to put an order on the set of edges. So now we are going to define an order. We consider an order, a partial order, on the set of edges. We are going to consider this order to define the transformation. And the order will be in such a way that two edges are comparable two edges are comparable if and only if they arrive to the same vertex. So this is an order that compares just edges which are arriving to the same vertex. So for example, we write the orders. Okay, I'm going to make something like this. For example, in this Bratteli diagram, I can say, okay, I have just one edge, so this is maximal and minimal. Here I have just one edge arriving to this vertex, this is maximal and minimal. Here I have two, so I can say this is the minimal, this is the maximal. Here, for example, I have three, and I can say, okay, this is the minimal, this is the successor, and this is the maximal. This is the way to define an order. And when we have this, we say that the diagram is ordered. So when we have this, we say that B, the diagram with this order, is an ordered Bratteli diagram. And now we...
When you fix it up.
Sorry?
Consider a set of edges.
Yeah, a total order here, yes. A total order in the set of edges arriving to the same vertex. Yeah. Sorry?
Is it right?
I'm going to talk about this after this because, okay, you can define any order that you want, but if you want to define this transformation, you need something special in the order. I'm going to talk about this now, in fact. Yeah. So, okay, before to say exactly what we need, there is one thing that we can here. For example, okay, suppose that I'm, okay, no, I'm going to say this in another thing. Okay, we are going to distinguish some elements in the set of infinite paths. So we are going to say that an element in the set of infinite paths is maximal if every edge is maximal. And minimal in the same way, but minimal. And okay, it's not complicated to see, this is the compactness of XB, that there are always elements in XB which are minimal, and there are always elements in XB which are maximal. So if we define X mean the set of maximal, okay, I'm going to say like this, the set of maximal, the minimal path, this is always non-empty. The same for the maximal path. This is always non-empty. But to define the transformation TB, we will consider orders such that this set contains exactly one element. So these are the orders that we are going to consider. And we say in that case that the diagram is properly ordered if there is only one element in X min and only one element in X max. And these are the orders that we are going to consider here. And with this, we can define the transformation. We are going to define TB in the following way. Okay. First, if X is the only maximal path, if X is the only maximal path, we are going to say that TBX is the only minimal path. And then if X is not maximal, we can look at the first coordinate, which is not maximal. So we are going to take k, the minimal coordinate, which is not maximal. And we are going to take the successor of xk in the set of edges that arrive to the same vertex. So we're going to say that fk is the successor of xk in the set of the edges that arrive to the same vertex than ak. And we are going to define tbx just as the infinite path that start with the minimal path from V0 to the vertex where fk start, fk, and then we continue with the same path than before. Sk plus 1, sk plus 2, and this is the minimal path from V0 to the source of fk. And what we are doing here this is the first part of the path x. So here we have xk, sk minus 1, x0. What we are doing with this transformation, we are taking exactly, okay, when you define this order in the set of edges that arrive to the same vertex, you can extend this order to the path arriving to the same vertex, just using the lexicographical order. And this transformation, the only thing that this transformation do is, okay, we take the path from x0 to xk, where k is like we define here, and then we take the successor of this path. This is fk, and this is the minimal path. We take the successor of the path x0, x1, xk, among the paths that arrive to the same vertex, and we change this path by this one, by the successor. And this is the transformation. This is TB. And with this transformation, okay, it's not complicated to show that this is continuous and also minimal when the Bratteli diagram is simple. So this is something which is not complicated to show. When B is simple, this is a minimal Cantor system. Okay, yes, from every, I'm going to talk about this now. To have this, you need B simple and properly ordered. And every time that you have a minimal Cantor system, any minimal Cantor system given by a C action, this system will be conjugate to a system like this. If your system, here there is something that I didn't say, but if the Bratteli diagram is not simple, or if the order is not like this, sometimes you can define also Cantor dynamical system. In fact, there is a construction from Medinet where he shows that every aperiodic Cantor system can be represented like this, where in that case, when your system is not minimal, B is not simple. Sorry? Uh-huh. What is that? Okay, in that case, this is not simple. And yeah, it's not exactly that I'm saying here. Yeah. Okay. So from a simple, properly ordered Bratteli diagram, you can always define a minimal Cantor system, and the converse is always true. So how can we do this? Using Kakutani-Rocklin partitions. Okay, so suppose that we have a minimal Cantor system. And suppose that you fix a non-empty Clopen set. For every point in C, you can see the first time that this point returns to C. So this gives you a function, the first return time map. This is well defined because your system is minimal. So you know that sometimes you will come back. And this function is continuous. So if you take a neighborhood of a point x in C, every point in this neighborhood will come back at the same time. So this will give you that the possibilities of return times are finite. Or in other words, the image by the function RC of C is finite. These are the possible return times. And you can use this to define a partition of the space. So the first thing that you can do is partition the set C, the Clopen set. And you can say, okay, I'm going to call Ci the set of all the points in C that come back at time Hi. And this will give you a partition of C. Well, I'm going to make a picture here. I don't know. Gracias. Gracias. Okay, so I'm going to try to make a picture here. So you have the set C, and then you have C1, C2, CK. This is a partition of C. And then, what happened with the image of this? You know, when you apply THI to CI, you come back to C. But in between, you are outside. And all the sets which are in between, they are disjoint. So you have this picture. TC1 here, T2, C1, until TH1 minus 1, C1, and then here you come back somewhere in C, and the same thing for the other sets. So you have this picture. And this picture gives you a partition of X. Every point in X is somewhere there. This is a partition of X. Because the system is minimal, everything is here. And this is called a Kakutani-Rocklin partition. This is a Kakutani-Rocklin partition. So every time that you have a minimal Cantor system, you can construct this. And now, how can we use this to construct the Bratteli diagram? Okay, if we can do this for a Clopen set, we can do this for a sequence of Clopen set. So now we take a sequence of a decreasing sequence of Clopen set, and we can do Kakutani-Rocklin partitions for every Clopen set. We can do this in a suitable way in order to get something that I'm going to write here. We can have the following. There exists always a sequence of Kakutani-Rocklin partitions sequence of Kakutani-Rocklin partition such that the partition n plus 1 is thinner than the partition n. The bases, okay, the set C is called the base of the partition P. These sets are called the towers. The HI are the towers of the length of the towers. And we can do this in order that the bases of the partitions are nested. With the intersection just only one point. And we can take this in order that all the set of this partition spans the topology. And okay. And when we have a sequence of partitions like this, we can define the Bratteli diagram. And how we can define the Bratteli diagram? So we take the sequence of partitions. So to construct the Bratteli diagram, Okay, we take a sequence of partition like this. And first, we are going to define the set of vertex. And in Vn, remember that here in the Bratteli diagram, we need to define the set of vertices Vn and the set of edges En. And to define Vn, we put one vertex in Vn for every tower in Pn. The towers are the towers are just this set without the decay here. So for every tower, we put a vertex. So here I'm going to say the tower 1, the tower 2, the tower Kn, because I have Kn towers. And then to define the edges, we need to see how the set of the partition Pn plus 1 are contained in the set of the partition Pn. And what happens if I see a tower of the partition n plus 1? Okay, suppose that here I have the picture of, I don't know, the tower K of the partition n plus 1. And for the first point, we know that every set here is contained in some set in Pn. But this is not contained in, these are contained in an ordered way. So for example, for the second point, I know that the first set here is contained in the base of some tower of the partition n. I don't know, this is contained, for example, in Cn, I don't know, just to say something, 2. And then the following is contained in the image of this, and the following in the image of the image, and so on. So at some point here, you will see that this piece is contained completely in the tower, in that case, 2 of the partition n. So you can think of this like a piece of some tower of the partition n. So I'm going to say this is contained in the tower n I1, I don't know. And then here you have the same thing. This is contained in the tower n I2, I don't know, and at the end, you have that all this piece is contained in some tower, n ik. And sometimes maybe if here you have the tower 1, maybe here you can have the tower 1 too. So the same tower of the partition n can appear many times here. And how you construct the edges from, for example, from Vn to the vertex k in Vn plus 1, for every okay, suppose that here we have the tower n, I don't know, 1. So for every time that you see the tower 1 here, you make an edge. Suppose that here we have, I don't know, just to, here we have 1 and here we have 2. Suppose that this is just like this. And here we have just this. So here you see 2 times the tower 1 of the partition N in this tower. So you put 2 edges from N1. And here you see just 1 time this tower in this bigger tower. So you put just 1 edge. And then you have the Bratteli diagram, but you don't have the order. And how you define the order? Okay, so the first edge will be the edge that corresponds to the first tower that you see here. So in that case, you see the tower 1. So you put 0 here. Then you see the tower 2. So you put 1 here. And then you see the tower 1 again, and you put 2 here. So this is the way to define the Bratteli diagram. And the order is given by the order where you see the towers of the partition N in every tower of the partition N plus 1. And this will give you a Bratteli diagram, which is simple because the system is minimal. In fact, if you take subsequence of the partitions Pn, the subsequence of the sequence of partition Pn, you can take Bratteli diagrams with positive matrices, strictly positive. And the order will be simple. The minimal path in this Bratteli diagram will be the point x0, and the maximal will be the image. The converse, sorry. It's the converse is the minimal. No, the maximal is the pre-image. And this is the way to produce a Bratteli diagram from a minimal Cantor system. So at the end, you have that there is a one-to-one correspondence between systems, or if you want Bratteli simple, properly ordered Bratteli diagrams. And minimal Cantor systems. But another thing that I didn't say, there is not only one Bratteli diagram for each system. So for example, if you take a telescoping of the Bratteli diagram B, and if you keep the order, so you get something which will be defined the same system. So there are many representations for the same system. But every time that you have a simple, properly ordered Bratteli diagram, you have a minimal Cantor system, and the converse is true. And for example, in the cases that, the example that I gave you yesterday, for example, for the odometer, suppose that you take an odometer in base Pn. When you take an odometer, you can construct Kakutani rolling partition with only one tower. So the Bratteli diagram that you will get here is something like this. Only one vertex, and the number of edges from Vn to Vn plus 1 will be just Pn plus 1 divided by Pn. This is a Bratteli diagram for an odometer. This is not difficult to construct. For substitutions, there is a result from Durand, Host, and Scow, where they proved that Bratteli diagrams which are stationary means that you have always the same incident matrices and the same order at each level. Stationary Bratteli diagrams correspond exactly to substitution minimal systems and stationary odometers. And stationary odometers means that Pn plus 1 divided by Pn is always the same, it's constant. And for toplet systems, you can find the stationary means that at each level, you have exactly the same matrix and also the same order. It's order and matrix. And for toplet systems, this is from Yer and Johansson. You can always find Bratteli diagrams with the property that if you fix the level n, the number of edges that arrive to each vertex in the level n is constant. This is called the equal path number property. And for many minimal Cantor system, you can find, I don't know, some special Bratteli diagrams. Okay, that's all. It depends if your system is expansive or not, because you can have a Bratteli diagram with the equal path number property which are not expansive. So these are not subshift. But you can always project this in an odometer. So these are exactly the system that have odometers as factors. But maybe they are not toplet because they are not expansive. No, if they are expansive, in that case, they are toplets. Yeah. Okay. I think everyone now remembers. Cool. I can put it again tomorrow.
this. Okay.
There's, and, okay.
Yes, okay. Okay.
Okay. And is there a pointer?
Yes. So this is the pointer. Okay. Forward and reverse.
So they will have Mike Boyle. That is